So let's talk about the periodicity of the elements. So, remembering that the periodic table is named for a reason, the periodic table is actually organized by electron configuration. So we call it periodic because the attributes or properties of the elements periodically repeat. So while they're not exactly identical, as you go down a group, right? We stack period on period. So as you go down a group, uh, everything in the same column is going to behave similarly. So once a period, you have a repeat of um, of a given element. Again, the properties are different, but they are similar. So all the alkali metals behave similarly. All the halogens behave similarly. Um, and the highest energy level that a element is on, meaning the n value, so the period that is on, contains the valence electrons. So if you remember when we looked at electron configuration, the valence electrons, you have the noble gas core, and then the valence electrons are everything after that. So potassium, calcium, scandium, titanium, everything in row 3, or sorry, row 4, is going to have argon as their core elements, and then all the electrons they have on that row are going to be their valence electrons. And the valence electrons are what are responsible for participating in reactions. And so because of this, because you have, again, if you're looking at electron configuration, because things end up having the exact same number of valence electrons, for example, hydrogen has one s electron as a valence. Lithium has your 2s1, right? Sodium is 3s1. Potassium is 4s1. So all of these in the alkali metals would have one valence electron. And because of that, they're all going to react similarly because they're all working with the same number of electrons for reactions. And so we can generalize a couple of trends that that we see across the periodic table. So the first one we want to look at is size. So atomic size increases as you go left and down the periodic table. So in other words, if you compare two elements, boron and carbon, boron is bigger, carbon is smaller. If you look at oxygen and sulfur, sulfur is bigger, oxygen is smaller. Because sulfur is below oxygen, so it's bigger. Boron is before carbon, so it's bigger. So you go decreasing size. As you go this way, you get smaller. Okay? And the reason for this is for going across the table, as you go across, right, Z star or Z, the effective nuclear charge, goes up, right? Meaning the same electrons see more protons, see a larger positive charge, so they're held tighter. So because of that, as you go this way, the electrons are being held in closer and closer and closer, and so you have a smaller atom. Whereas as you go down the column, you're adding an entire electron shell. So as you go from the n equals 2 to n equals 3, I've added all of these electrons to go from here to here. So of course, those are naturally going to get larger. So atomic size increases up or left and down. So it decreases up and to the right. So as you go up and right, it gets smaller. So ion size is a little bit different. And basically, keeping in mind that basically your size is dictated by your electrons, because the nucleus relative to the amount of space the electrons are taking up is very, very, very small, and then the electrons take up a ton of space. So the nucleus doesn't really factor into the overall size of the atom because the electrons take up such a large amount of space. So like if you think of the sun relative to the size of the galaxy going out as far as, or size of the solar system going out as far as Pluto, right? The planets are spaced out way further relative to the size of the sun. So it's an okay analogy. It's not a great analogy, but that's the idea, right? So it's like the number of planets is going to really depend. It's going to tell you what size a solar system is, more so than the size of the sun, if that makes sense, if that analogy is working for you. So cations get smaller because they lose electrons, and anions get bigger because they gain electrons. So lithium has a atomic radius of 1.28 picometers. Lithium plus has an atomic radius of 0.76 picometers. So lithium gets smaller, sodium plus gets smaller, potassium plus gets smaller. Beryllium 2 plus gets even smaller. Magnesium 2 plus gets even smaller, even smaller. And again, you're seeing the trend here. Lithium is 1.28, beryllium right next to it is 0.96 because even though this has one extra electron, it has an extra proton, so it's sucking them in closer. On the other hand, right, on the other side of the table, you have your negative ions. Fluorine gets much, much bigger. Of course, fluorine is teeny tiny. Fluorine gets much, much bigger. Chlorine gets much, much bigger. Bromine gets much, much bigger. Okay, so negative ions big, positive ions small. And the degree to which they get larger or smaller depends on the size of the charge. So +1 is bigger than +2 is bigger than +3. So +3 is going to be your tiniest, then +2, then +1, then -1. Then -2 will be bigger, then -3 will be the biggest. Okay, so that's the trend for ion size. So it's less to do with its location because you got to compare stuff that's basically on the same period or it doesn't work. But it's going to be the size of the charge. If it's a positive charge, it gets smaller. If it's a negative charge, it gets bigger. And then the more of the charge, the bigger the charge is, the bigger or smaller it gets depending on whether it's negative or positive. So the most positive ion is the smallest. The most negative ion is the largest. Okay. There's two more trends we need to look at. The first one is called ionization energy. Ionization energy is a measure in kilojoules per mole of how hard it is to pull an electron off of an atom. So if I wanted to go from sodium to sodium plus an electron, it takes energy to remove electrons. So basically, you can basically calculate this. You can find this experimentally and say, oh, it takes 400 kilojoules or whatever it is to remove one electron from sodium. And each subsequent electron is going to be harder to remove. So each subsequent electron is harder to remove. So to go from magnesium to magnesium plus takes X amount of energy. To go from magnesium plus to magnesium 2 plus takes more energy. And based on the energy ionization charge, you can actually figure out what the cation charge is because at a certain point, you will see a huge jump between one electron and the next electron. Based on that jump, you can tell what the charge is. So let's look at a couple of elements. So we have sodium, we have magnesium, and we have aluminum. So we know sodium usually goes to +1, magnesium goes to +2, and aluminum goes to +3. So we look at the first ionization energy for sodium, it's 494, and the second one is almost 10 times as much, 4,500. Third and fourth don't really matter. We look at magnesium, the first is 736, which is more than this one. The second is about double that, 1450. And then the third is 8 times that. Okay, so you get a huge jump, right? So this is a huge increase. This is a little increase, and then this is a huge increase, right? So then for aluminum, 577, triples to 1820, not even double to 2740, and then huge jump up to 11,600, right? So little jump, big jump. When you see that big jump, that means you're not this electron, that stays, which means you're only going to take the ones that came before it. So since the big jump, you get 3 electrons and then big jump, that tells you that it's a +3 ion. You see 2 electrons gone, then a big jump, you see that's a +2 ion. You see 1 electron, then a big jump, then that's a +1 ion. So from the ionization energy chart, you can actually identify what the charge on the ion is. Okay. So this property increases as you go up and to the right. Okay, so it's the opposite of size. It increases as you go up and to the right. So as size decreases, ionization energy increases. Now this makes sense if you think about it, because if you're holding your electrons in closer, it's going to be harder to pull them away from you. So smaller size means higher ionization energy. Okay, we can also talk about electron affinity. Electron affinity is kind of the opposite of ionization energy in terms of what it represents. And electron affinity is how much an atom wants another electron. Okay? So the reason I say that rather than like giving an electron to another atom is because we also measure this in terms of kilojoules per mole, right? We measure the enthalpy of this half reaction, right? So fluorine plus an electron giving me fluoride minus. It can be negative. So my enthalpy can be negative. It can actually be a good, like a favorable reaction where I get energy out because it's remember, everything wants to go into the most stable possible configuration. If the ion is more stable than the neutral atom, then this is going to be a spontaneous favorable thing. Versus going like from sodium to sodium plus, it might be easy, but you still have to put energy in. So you can actually get energy out from electron affinity. So electron affinity can be negative. It can also be 0. Noble gases do not have a defined electron affinity. It's not 0. It's not 0. It's not defined because noble gases do not have any electron affinity. You cannot add an electron. And again, because the kilojoules per mole, right, the lower it is, the more favorable it is. So 0 is actually not bad as far as electron affinity goes, right? So that means it's, enthalpy neutral, but you're not getting energy and you're not getting energy out, but you don't have to put energy in to make the reaction go. It doesn't mean that it's not taking the electron. So noble gases don't have an electron affinity of 0. They just don't have an electron affinity. There is no number. It is not defined. Na, not defined. So not 0. It's undefined. And this one increases right and up just like ionization energy, which again makes sense. If you're less likely to give up an electron, then you're probably more likely to take an electron. So to summarize, atomic size increases down to the left. Ionization energy and electron affinity increase right and up. And then the ion size depends on the charge. More positive is smaller, more negative is larger. So, which is larger between boron and fluorine, magnesium and barium, sulfur and tantalum? So here we need to look on the periodic table. So we look at boron and fluorine. So boron's here, fluorine's here. So fluorine is to the right of boron, so fluorine's going to be smaller, boron's going to be larger. Magnesium and barium, we look here, magnesium, barium. Barium is below magnesium, so barium's going to be bigger. Okay, so boron is bigger, barium is bigger. And then sulfur and tantalum. So sulfur is S, tantalum is Ta. That one's right here. So tantalum is down and to the left, so tantalum is bigger. Which has the highest ionization energy between sodium and phosphorus, carbon and tin, tungsten and bromine? So sodium, let's clear these. So sodium and phosphorus, or sorry, yes. Whoops. That's sulfur. So sodium here and phosphorus there. Sodium is to the left of phosphorus, right? So phosphorus has higher ionization energy and electron affinity. Carbon and tin, so higher ionization energy is going to be phosphorus. Carbon and tin and tungsten and bromine. Okay. Carbon and tin, right? Carbon is above tin, so it's going to be carbon. And then bromine and tungsten. Bromine and tungsten. Bromine and tungsten, okay? So bromine is up and to the right, so it's going to be bromine. So carbon, phosphorus, bromine. And then which has the highest electron affinity between niobium and tellurium, potassium and cesium, vanadium and krypton? So potassium and cesium, higher up, right? Or niobium and tellurium, potassium, yeah. So potassium, niobium, tellurium, and then vanadium, krypton. Okay, so niobium is here. Tellurium is all the way over here. So this is to the right, so it's going to be tellurium. And then vanadium and krypton. Okay, so vanadium V and krypton Kr. This is kind of a trick question. The answer is vanadium because krypton, not defined, does not have an electron affinity. Okay, finally, order the ions from smallest to largest. Potassium plus, K plus, P3 minus, Cl minus, Ca2 plus, and S2 minus. So smallest is going to be 2 plus, so that's the smallest. Then K plus, then S2 minus, then Cl minus, then S2 minus, then P3 minus. So it's going to go calcium's the smallest, then potassium, then Cl minus, then S2 minus, then P3 minus. And that's pretty much it for periodic trends. They are pretty straightforward. Again, the periodic table gives you all the information that you need.